Hello and welcome. In today's video, we are discussing about Python trees. So let's see the definition. What is a Python tree? Python tree is a hierarchical data structure that consists node connected by its edges. So tree is a hierarchical data structure. It consists of nodes and then connector. Then the connector can be multiple. That means one node can connect to two other nodes. So as a node contains a value and references to its child nodes. So it is a similar data structure to linked list. As linked list contains data that can be linked to other nodes using the next pointers. So we have previously covered data structures like array, linked list, stacks and queues. These are all linear structures, which means that each element follows directly after another in a sequence. Trees, however, are different. They are not sequential, but they are hierarchical. A tree's element can have multiple next elements. So it will point to its children using multiple next, and then the data structure is called a tree because it looks like a tree. Let's see a sample how it looks like. Let's say we have a root node and it points to its child node, which is A, and it points to even it has another child. It can be, can have another child like B, and it can have one more child C. So it can be pointing to multiple other nodes which are called as its children. And then it continues. It has a child D, and it has another child E. So likewise, we can have multiple child to each child node of root element. If you see, B has F, G, it can even have more, more than two children like H and I. So we have child B has four children F, G, H and I. So as each node have multiple children and one root references to three other nodes and A refers to two other child nodes. C doesn't have children and B has four child nodes F, G, H and I. So this looks like nothing but a tree. So let's see what are the use cases that we will be implementing using Python trees. Let's go to the use cases. First use case is number one, hierarchical data structures. For example, file system, organization, models, and many more. Number two, data bases. Because we use hierarchical tree approach for databases because it is quick data retrieval using tree methods. And three, routing tables. So as routing tables can be implemented using trees because it is used for routing data in network algorithms. And fourth use case, sorting slash searching. So it is used for sorting data and searching data also because it's hierarchy. Number five, priority queues. Priority queue data structures are commonly implemented using trees such as binary heaps. Let's look into more in detail in further sections. Before that, we will discuss about major type of trees. Just now you have seen general tree which is shown in this diagram. So each root has a children and child node has its children linked using the next pointer like this. So this is a generic tree and we have three major tree types used to represent hierarchical relationship. So first one is binary trees. Binary tree is nothing but each node has up to two children. Means 2 is the maximum child a node can have and the left child node and the right child node. One is called left and another is called right. This structure is a foundation of more complex trees types like binary search trees and AVL trees. And the second type of tree is called binary search trees, simply called BSTs. A type of binary tree where for each node the left child node has a lower value and the right child node has a higher value. So left is lower, right is higher value. So it is easy for fetching the values in binary search tree implementation. And what is the third type? AVL trees. A type of binary search tree that self-balances so that for every node, the difference in height between the left and right subtrees is at most 1. This balance is maintained through relations when nodes are inserted or deleted. So difference in height between left and right subtrees is at most 1. So each of these data structure are described in detail in further sections. So let's discuss about AVL trees more. Why we call them as AVL trees? It is named after its inventors Adelson, Pilsky, and we have another inventor. His name is Landis. So it is named after the inventors. Its self-balancing binary search tree with the difference 1 made it very usable in particular cases where the balance factor comes into the picture. So now let's look into the differences of trees from arrays and linked lists. So we can basically say the benefits of trees over arrays and linked lists. Number one is arrays are fast when you want to access an element directly, like element number 700 in an array of 1000 elements, for example. Means if you want to fetch array of 700, it is very quick. But inserting and deleting elements require other elements to shift in memory to make place for the new element, or to take the deleted elements place, and that is time consuming. Whereas linked lists are first, when inserting and deleting nodes, no memory shifting is needed, but to access an element inside the list must be traversed, which increases O of n time complexity. Whereas Python tree, like we have seen the type binary trees, binary search trees, and AVL trees are good compared to arrays and linked lists because they are both fast at accessing at a node and fast when it comes to deleting or inserting a node in the tree with no shifts in the memory required. So those are advantages of trees over linked lists and arrays. So that's all about trees in Python. You can summarize based on the tree type what are all the use cases. If I see general trees, they can have unlimited children, unlike binary tree has only two children, and we even have balanced tree which has two, AVL tree which has two children max, and we have many other type of trees that we will be looking into when we do problem solution, among which full binary tree, complete binary tree, and n array tree are the other types we will be using. So for full binary tree, it is max 2 or 0 children. An array has n number of children, and complete binary tree has again 2 max children. And we use general trees for file systems, binary trees for parsing, recursion trees, full binary tree for static structure, complete binary tree for binary heaps as we discussed before, balanced tree, search, real-time systems, BST for database indexing, AVL tree, high-speed search using trees, N array tree. It is for AI and gaming. So let's look into some programmatic implementation. How do we do insert operation in a BST? For that, we first must need to define a tree, either binary tree or BST or general tree implementation we have to do. Let's look into the Python binary trees. So for doing implementation of binary trees, there are few restrictions that a node can have maximum of 2 children, which gives many benefits in our use case. Algorithms like traversing, searching, insertion, deletion become easier to understand using the binary tree that has nodes with maximum 2 children. It is easy to implement and it runs faster than other types. Keeping data sorted in a binary search tree makes searching very efficient because left is lower, right is higher. It makes very quick searching using this method. Balancing trees is easier to do with a limited number of child nodes using an AVL binary tree, for example. Binary trees can represent as Python arrays, making the tree more memory efficient. So as we have seen, binary tree implementation looks like this, but each will have maximum 2 children. So that is diagramical representation. Let's write a class to create binary tree. Let's begin with the class definition. Class tree node init method self comma data for the node self comma date self dot data equal to, we have to assign the data passed, and we even have self dot left equal to, initial it is none, self dot right is also none. And let's start creating nodes. Root node equal to tree node of, like before, we will mention root and node, first node, which is a child node. We will create node A equal to tree node of A. Likewise, we will be creating node B, node C, D, E, F, and G. So, likewise, we can create more nodes. So, after creating node root and node A, B, these two are children to root. Let's link them. Root dot left equal to node A. Root dot right equal to node B. That is how it is here. Let's remove this because it has to be only two children. You have to create DE and link it to A. So we have DN and we have F and G. F, F and G. So now we need to link node A dot left equal to D and E. Node D, node A dot right equal to node E. So that is how D and E is connected to A. And node B dot left equal to node F. Node B dot right equal to node G. So as we have in the diagram, node B dot left is F, node B dot right is G. That is what we have done here. So now the tree is created. We can test this by executing, and we can how we can traverse any element in this diagram. If I wanted to fetch element E, then it becomes root dot left dot right, and then D becomes root dot left dot left. Likewise, root dot B is right, root dot right is G, root dot right dot left is F. So if I want to print, let's say E root dot right dot, sorry, root dot left dot right. So if I want to print D root dot left dot right dot data, which is value for E. You can try executing this code and see it has to print E. So that is how you traverse in a binary search tree. As we discussed before, binary trees are balanced, complete, full binary, and one more perfect binary tree with its own features, wherein balanced has how many children for each node? At most one in difference between its left and right subtree heights, and complete binary tree has all levels full of nodes except the last level, which is can also be full or filled from left to right. Full binary tree is a kind of tree where each node has either 0 or 2 child nodes. And we have even seen how to traverse to a particular node. There are certain methods, BFS and DFS. We will be looking into those techniques along with programmatic example in further videos. How do we traverse using BFS and DFS in binary trees? And let's move to binary search tree. And let's look into example of binary search tree. So it is also similar to binary tree, but binary search tree will have left as lower, right children as higher to the root node. So let's take the same example. Let me create a method in order traversal and implement it. Let's copy from the previous example and see. This is the example for binary search tree. So we have defined tree node as before. We have taken from the previous code and we are adding data, adding left, adding right nodes, and then we have another method called in order traversal. What it does, it checks if node is none, it just returns, and then if the node is not none, then it calls recursively the in order traversal tree to fetch its children. So what is it is doing here? If node is none, that means there are no nodes in the tree, so returns nothing. If node is not none, it makes a recursive call to the self method itself with node dot left. It goes to left side and then prints node dot data, and again it calls node dot right. So that is how it traverses through using this function. Now when we create tree node 13, so let's draw root node becomes 13 and node 7 tree node 7 15 3 8 14 19. So we are creating these nodes and we need to link root dot left node 7. So this is 7 and root dot right node 15. 15. After this, node 7 has children 3 and 8. 3, 8. And node 15 has children 14 and 19. 14 is lower, so left. 19 is higher, so right to 15. And then they have even one more node. Node 19 dot left is 18. So here we need to write one more node which is 18 left of 19. So we have created the tree, binary search tree. Now if I call in order traversal route, route is nothing but node 13. So if I say route becomes 13, what it takes first, it gives 13. If 13 is not none, if 13 is none, it is false. So it will not return. It goes and calls 13 dot left, which is 7. This is 7. And immediately after calling, it goes to here, take 7. Node is none. No, it is not. So again left. 7's left is 3. So when it becomes 3, again it goes here. 3 is none, false. Again 3 dot left. 3 dot left is none. So it takes none here. Node is none. True. Return. So it comes here. It travels to extreme left of first root node and print node dot data. So now it prints node dot data. So after traversing, it will have, when it is becomes none, it returns. So and then the node dot data becomes 3 and it goes back to the previous step 7 and then